Hello and welcome to this new video. In this new video, we are going to start section 2.2, where we'll have so many interesting and new results. We'll start with the notion of index of a loop with respect to a point not in the loop. Okay, so the target is to define an integer that counts the oriented number of times the loop winds around the point not in the loop. Okay, so let us start with a figure. So here I have a piecewise smooth loop gamma. Suppose we can start with any point actually. So suppose you start with here. So, and you have 3 points actually. If you consider the point in red, then intuitively the loop does not wind around that point. So this index should be 0. If you consider the point in white, then actually the loop winds twice about that point, right? And if you consider the point in yellow, then you should convince yourself that gamma winds one time, because here the orientation is in the trigonometric sense, so counterclockwise. So the index of gamma with respect to the red point should be 0. The index with respect to the yellow point should be 1, and the index with respect to the white point should be 2. Okay. Now, nothing prevents that the loop winds more than once. So here I put a double arrow to indicate that the loop is traveled or traversed twice. Okay. So in this case, we still have that the index with respect to the red point is 0. Now the index with respect to the point in yellow is 2, because we moved twice actually, if you follow the orientation. And the index with respect to the point in white should be 4 this time. Okay. Now, if you reverse the orientation, then the index with respect to the red point should be 0 still, and the index with respect to the white to the yellow point should be -1. Okay, because we are going in the clockwise direction, which is considered to be negative. And the index with respect to the white point should be -2 actually. Okay. Now I chose an arbitrary point. The red point here could be anywhere in what we call the unbounded component of the loop. So if you consider, so this is the complex plane. If you remove from the complex plane gamma or gamma star, then we are left with 3 connected components. The unbounded component, or the component containing infinity, this component here, right, which is between these two, and this component. So we see that the position of these points can be arbitrary in each component. So if I take any point here white, then the index should be the same. And same thing if I take the yellow point anywhere here. Okay. And this is precisely what we are going to do actually. So now I don't know who invented the formula. I'll give you the formula actually. I don't know who invented it, but actually you can search for it if you are interested. Where does this formula come from? So let us read it first. So the index of a loop gamma with respect to a point not in the loop is 1 over 2 pi I times the integral over gamma of dz over z minus a, which is by definition equal to this formula. And so it's called the index, or the winding number of gamma with respect to a. Okay. Now, what I'm going to do is to justify this definition later, but let us first try to understand it. Okay, so let us start with a simple example, the simplest example of a circle, the simplest loop possible. So take the circle of center A and radius r. So the parameterization is given by this formula, as you know, and t is between 0 and 2 pi. So the circle is traveled just once in the counterclockwise or trigonometric direction. Now we could take t to be between 0 and 4 pi if you like. So, but let us start with this case. Then if you apply this formula, this is the definition of, so it's just 1 over gamma t minus a times gamma prime here. So gamma t minus a is just REIT, and the derivative is RIEIT. So the EIT cancel, and the I cancel, the 2 pi cancel, the R cancel, so we are just left with 1. So now it's not always easy to compute indices in this way, but we shall learn methods to compute them. Okay. Now, if I took t between 0 and 4 pi, so the circle is traveled twice in the trigonometric sense, then I get here 4 pi, so I get 2. And this corresponds to our intuition. If I take e minus it, so counterclockwise, I will get -1, and so on. Okay. So this is the index of the circle, the simple circle, with respect to its center. It's always 1. Okay. Now, let us prove that this formula actually gives an integer. So this is not a coincidence. It will always give an integer. Okay. It could be negative. But before I'm going to do that, I need two things about the exponential function. First thing that you probably know is that the solution of the equation Ez equal 1 are exactly 2n pi I, where n is an integer, positive or negative. Okay, so I have infinitely many solutions. And the second property that I will use is that the exponential is surjective from C to C star, which means that I can always solve the equation E alpha plus I theta equals Z. Okay, if you separate the real and imaginary part, you get E alpha equal modulus of Z. So alpha is necessarily the len of the modulus. Of course, so for Z in C star, so the modulus of Z is not 0. So this makes sense. And you can take as theta any argument of Z. Okay, so EI theta is actually Z over the modulus. Okay, you may take the principal determination of the argument, but you can take any other. So we see here that since the angle is measured at so two angles differ by a multiple of 2 pi, so we see here that you have infinitely many solutions of this equation. Okay, all differ by a multiple of 2 pi I. Okay, and now let us prove that the index given by this formula is indeed an integer, not trivial from the definition. Okay, so as we know, we can always assume that our loops are based on 0, 1 by a change of values. It's not a big deal. So consider a piecewise smooth loop defined on 0, 1. So gamma 0 equal gamma of 1. And A is not in the image of the loop, okay? Because otherwise, this integral is not defined. So the denominator should not vanish. This is why we assume that the point is not in the loop. And now consider this function g of t to be the exponential of this integral from 0 to t of gamma prime of s over gamma s minus a with respect to ds. So this is actually a function of t, and t varies between 0 and 1. Okay. So of course this is related to this form actually, but here I let the bounds vary. Don't worry about the points where gamma does not possess a derivative. It's not really important. Actually, if you want, you can assume that gamma is just smooth. It doesn't change anything. So suppose gamma is smooth, then G actually has the same smoothness as gamma, and I can apply the chain rule. So we know that the derivative of the exponential is itself. And so the chain rule tells me that I have to multiply this by the derivative of the integral. But the derivative of the integral is just what is inside. This is the fundamental theorem of calculus, actually. So the derivative of this guy here is just what is inside, evaluated at the point t. And I get, so the exponential is just g of t, and the second term here is just gamma prime over gamma t minus a. So I can write as g of t over gamma t minus a times gamma prime. So if you consider the quotient g of t over gamma t minus a and call it phi. Now recall that g has the same order of smoothness as gamma. So to simplify, you can assume that all are smooth enough. It's not a big deal, actually. So we can differentiate by the quotient rule. Okay, so the derivative of phi is the denominator squared, and the numerator is g prime times the denominator minus g times the derivative of the denominator. So we get this formula. But this equation here, g prime equal g over times gamma prime over gamma t minus a, actually tells me that the numerator is 0. Okay, because if you multiply by gamma t minus a, these two are equal, so the difference is 0. And okay, if you assume that the loop is smooth, then we can conclude that actually phi is constant. If you don't assume that it's smooth, we just can say that phi is piecewise constant. So okay, but not necessarily the same constant. However, because gamma is a loop, so gamma 0 equal gamma of 1, right? Yeah, so we know that phi is constant, all right? So in particular, phi of 1 equal phi of 0, okay? So if I replace, what is phi of 1 actually? Is g of 1 over gamma 1 minus a. But g of 1, if you go back to the definition, g of 1 is just the exponential of the integral from 0 to 1 of gamma prime. And by definition, the integral from 0 to 1 of gamma prime over gamma s minus 1 just 2 pi r times the index, because the index is 1 over 2 pi r times that integral. Just follows from the definition. Okay, so this integral actually put 0 here and 1 here. So the integral from 0 to 1 of gamma prime s over gamma s minus 1 is 2 pi r times the index. And phi of 0 is actually g of 0, but g of 0 is just 1. If you go back to the definition, the integral from 0 to 0 is 0. Exponential of 0 is 1. So I get this equation. Exponential of 2 pi r times the index over gamma 1 minus a equal 1 over gamma 0 minus a. Now, since gamma is a loop, gamma 1 equal gamma 0, as you observe. So these two cancel, and we are just left with the equation exponential of 2 pi I times the index equal to 1. And according to our previous remark, this just means that 2 pi I times the index is a multiple of 2 pi I. So the index is really an integer. Okay. So this proves the first result, that the index is really an integer, but it was not trivial from the definition because it was given as an integral of a complex variable. Now, having said this, and so I will just use this notation now, I can justify the definition of this index, why it counts the number of times the loop winds around that point. Okay. So it's oriented, as we saw in the introduction. Okay. So call this function actually that was inside the exponential f of t. Okay, so g is just the exponential of f of t. Okay, so as you already observed, f is differentiable and the derivative is just what is inside. We already did that. Okay, except at finitely many points, don't worry about them, not change anything. So g of t is just the exponential of f of t according to our notation. And this is just actually, we observed that g of t is just gamma of t minus a over gamma 0 minus a. Okay. Now, since the exponential is surjective from c to c star, and 1 over gamma 0 minus a is not 0, so we can find a complex number c whose exponential is this number. Okay? Surjectivity of the exponential function. So therefore, when I multiply by, so how can I write that? I can write EFT equal gamma t minus a times EC. So this is one. So okay. So when I multiply by e minus c, I get this equation. So the exponential of ft minus c of this constant equal to gamma t minus a by this equation. And now once again, one more notation. Call this function ft minus c h. Okay. So everything is smooth here. So okay. So then we get what actually? Then, as we said, so h prime equal f prime, but f prime is gamma prime over gamma t minus a. So h prime of t equal gamma prime of t over gamma t minus a. Yeah, I know the notation is a little bit heavy, but you'll get used to it. And if you, so ft minus tc is just h, so I can write this equation as e to the ht equal gamma t minus a. Okay, now later I will denote the real part of h by alpha and the imaginary part by theta, as we did before. So this equation becomes e to the alpha t plus I alpha theta t equal this guy. Okay. Okay. Therefore, if you look at the first point, the integral from 0 to 1 here actually of gamma prime over gamma t is just the integral of h prime, right? So this is just the index multiplied by 2 pi I. So the index actually, as if you recall, is what? Is 1 over 2 pi I times the integral of this guy. So, so the index is 1 over 2 pi I times the integral of h prime. And once again, by the fundamental theorem of calculus, this is the integral is h of 1 minus h of 0. So it's just the variation of h. Okay. And now, as we said, if we go to the second point here, as I was saying, if we call alpha of t the real part of h and theta the imaginary part, I get this equation actually. So e to the alpha t plus I, yeah, it's written here actually. So this is point 2 actually. So e to the alpha t times or plus ei theta t is gamma t minus a. This is the equation of point 2. Okay. And necessarily, actually, that we saw that e to the alpha t is just the modulus of this guy. So alpha t is the len. Everything is well defined here. Okay. Now, since gamma is a loop, then gamma of 0 equal gamma of 1, and therefore alpha of 0 equal alpha of 1. This is first thing. So alpha doesn't change. Okay. So what is the difference? This is not 0 in general. It could be 0, but it's the variation of h. Therefore, if I go back to the definition of h, since the real part cancel, so I get that h1, the variation of h between 0 and 1 is I times the variation of theta, which was the angle actually, as we saw, okay, of gamma t minus a. Okay. So I simplify by I here, if I go back to this equation and replace the variation of h by I times the variation of theta, the I cancel, and I'm left just with this simple equation. It tells me a very important thing. It tells me that the index is 1 over 2 pi I times the variation of the angle that gamma t minus a makes with the positive x-axis. So it's the variation of the angle. So And that's it. So the variation of the angles actually divided by 2 pi is an integer that tells me how many times I traveled around A and in which direction as well. Okay, and that's it. So this justifies the definition of I, of the index. Okay. Now, if you didn't understand everything, don't worry, because in applications, we'll just take this very simple case where gamma is a simple loop. When gamma is a simple loop, so doesn't have double points, then the index and A is inside, then the index is just either 1 or -1, depending on the orientation. Okay? Most of the time, we'll choose the positive orientation. Okay, but you could also choose the negative orientation. Okay, so in the exercises, we shall just justify actually why this is so. Okay, but in the applications, just take I to be plus or -1, sometimes 0 if A is outside gamma of the simple loop. But the discussion that I made here actually is very general. Okay, so the loop is not necessarily simple. Okay, so this concludes this remark about the justification of the index. Okay, now I suggest that you stop the video and do a small exercise to test your understanding by going back to the definition. So we know that intuitively, when we change the orientation, the index becomes the opposite. Okay, this should be intuitively clear, but I want you to prove that by going back to the definition. Okay. And second thing, if I take the circle of radius 1 and center 0, but traveled n times, okay, when n is an integer, then find the index. Intuitively, it should be n, because we travel the circle n times, okay? It should be n, but prove that by going back to the definition. I could have taken EIT, t between 0 and 2n pi, same thing. And more generally, you can generalize this. So this is C. If gamma is a loop, okay, extended by periodicity, because gamma 0 equal gamma of 1. So we can extend it by periodicity to the whole line. And then set mu of t to be gamma of nt. Okay, so this means that mu is the same loop, but traveled n times, where n is an integer. Could be positive or negative. So show that the index is then multiplied by n. All this should be intuitively clear, but I want you to prove that by going back to the definition. Okay, so take a break and do this. And after you finish, we could continue. Next result is that what we said in the beginning is that the index is constant on the connected components of the complement of gamma. If you just go back to the figure of the beginning, so I told you what is, so gamma or gamma star divides C. We say that gamma star divides C into connected components. So in the first example, we had 3 connected components. One of them was unbounded. Okay. So, and we observed that by our interpretation of the index, it doesn't matter which point you take inside the same, as long as it belongs to the same component, okay, the index should be the same. I will prove that now rigorously by going back to the definition. Okay, call this function, so I call it zeta here, so, or you can call it function of A if you like, so call this f, okay? So when zeta varies, okay, we get a function, but this function takes integer values. And so it's continuous, it takes connected sets into connected sets. So it takes components to components. But what are the components of Z? Z is discrete. So the only connected subsets of Z are the one-point sets, the singletons. So this means that the image of every component is just a singleton. And this precisely means that f, which is the index, as a function. So gamma is fixed in this reasoning, but zeta varies. So it means that f is constant on the connected components of the complement of gamma. So this is a topological argument, actually. But if you don't like this reasoning, we can prove this analytically. So as you said, put f of zeta to be the index, and go back to the definition. Now we have an integral depending on a parameter. And if you recall the last result of section 2.1, this function is actually holomorphic as a function of zeta. So it doesn't depend on z, it depends on zeta actually. Okay, because z1 over z minus zeta is actually holomorphic, so continuous in both variables. So, and by the way, the denominator does not vanish because zeta is not in gamma. So we can differentiate under the integral. So the derivative of the integral is the integral of the derivative. So the partial derivative of this guy with respect to zeta. And the derivative of what is inside is 1 over z minus zeta squared, because the minus cancel. Okay. Now, the function inside has an antiderivative, of course, as you know. And one antiderivative is given by minus 1 over z minus zeta. And therefore, by Barrow's rule, the integral is 0. Okay. Therefore, so f prime of zeta is 0 on outside gamma, of course. And this precisely means that f is constant on the connected components of the complement of gamma. Now, we cannot conclude that gamma is the same constant everywhere because it may change from component to component, okay, as we saw in the first example. So always keep in mind the example with which we started. This constant can vary, actually could be the same, but can vary from component to component. And this is important, actually. And this is a point where students may be confused. If f is constant, the derivative is 0. Now, if the derivative is 0, we cannot conclude that it's constant. It's constant if on every connected set, if you like. Okay, we need connectedness here. And this is something that you can prove by going, if you study differential calculus, you will see why in this case, actually, because you have something like the mean value theorem that tells me that if f prime is 0, then f is locally constant, if you like, but need not be globally constant. Okay? And maybe later I will give you an exercise about this because it's important to work on connected components. Okay? Think of, for example, the function which is -1 for x negative and +1 for x positive. Okay? As a function on R star, its derivative is 0, but it's not constant. It's constant on the connected components of R star, which are 2 actually. So, okay, last result that was intuitively clear, that the index is 0 on the unbounded connected component. Okay, so the complement of gamma has always an unbounded component, which contains infinity, if you like, and the index is 0. Why this is so? Because since gamma is continuous, so gamma star is the continuous image of the compact set 0, 1, so it's bounded. Therefore, so I can put my loop inside a ball, okay, a ball of center 0 and large radius, okay. And now take a point outside this ball, so it's already, of course, outside gamma, okay. Now, if z is in gamma star, and if you apply the second form of the triangle inequality, so z minus a in modulus is bigger or equal than absolute value of modulus of z minus modulus of a. So when you take the inverse, you get the same thing. And now, if z is in gamma star, then the modulus of z is less than r. So minus the modulus of z is bigger than minus r. So you get actually that this quantity here is less than 1 over modulus of a minus r. Okay, so because modulus of z is less than r. Okay. And therefore, if you apply the fundamental estimate, if we go back to the definitions, the modulus of should be here one arrow. So the modulus or absolute value of the index is there is an error here. It's 1 over 2 pi I actually. There is a 1 over 2 pi here. Doesn't matter. So we have the modulus of the integral, but the modulus of the integral is actually less than the length of the path divided by the supremum or any bound of the function inside. But the function inside is bounded by 1 over modulus of a minus r. So there's a constant here, 1 over 2 pi, but doesn't change anything, because now when so a is actually, we know that it's constant. So if we let so r is fixed here, but if we let the modulus of a tends to infinity, then this tends to 0, and therefore the index is 0. Okay. So this is a rigorous proof of the fact that the index is 0 on the unbounded component of the complement of the loop. Okay, so I think I'll start here for this video. And next video, I will prove one of our main results of this course, the analyticity of holomorphic functions. And by the way, since we don't have enough time, actually, I'm obliged to make more than one video per week. So I will post another video. So sorry for that. But when we started slowly, and then we were told that we should finish in July 11. So we don't have enough time, actually. So you should do some effort, actually, because we have to finish the program. Okay. So thank you for your attention, and see you next time.